Okay, hi everyone. We are moving on to the next unit in the course. And what I would say this is solving the Schrodinger equation and applying the postulates of quantum mechanics to model systems. Atkins calls this translational motion, sort of the first model system. I think more generally, I would refer to this as particle in a box, right? That's what we're talking about. This is really important. It is the canonical model which illustrates the essential features of any quantum mechanical system. If I had to pick one thing for you to learn in the course, this would be that topic. And I'm going to summarize this for you here. But one of the key ideas is that when particles become confined in space, their energy levels become quantized and the wave nature of the particle emerges. The second major point is as the box gets bigger, the energy separation decreases. And this is a specific equation that we'll derive later in the semester. This is an example of those ideas. It's from my research lab. These are semiconductor nanoparticles. They glow different colors of light, as you can see here. And what's different about these particles is the size. Right? Some are 2 nanometers in diameter, some are 4. And what you see is that as the particle gets bigger, the color they glow shifts to longer wavelengths. Right? Energy level separation is decreasing. So before we get into all of this, I'm going to actually start with another model, which is called a free particle. The free particle, the results from it really aren't all that important. We're not going to use them frequently, but it's a really useful system to illustrate the process and gives us some important comparisons. Okay? So let me talk about the process that we're going to use to solve all the problems in the course. Wave function contains all of the information. Wave function is defined by the Schrodinger equation. And so when we solve the Schrodinger equation, these are the 3 things we're going to do. We are going to write the Schrodinger equation for the specific problem involved. We're going to solve it, and we're going to interpret it. Right? Those are the 3 steps every single time. And so let's talk about this. Here, I am showing you the most condensed form of the Schrodinger equation. In its most condensed form, it's H psi equals E psi. Remember that H hat is the Hamiltonian. It is the total energy operator. It has a kinetic energy component. So I should write here. This is the kinetic energy component. And this is the potential energy component. The kinetic energy component is common to all systems. It can take slightly different forms depending on the nature of the problem, if it's 1D or 3D or Cartesian or polar or whatever. But all systems have kinetic energy. And then the potential depends on the specific context. Because this is common and this is unique to each set of problems, this is really what defines the problem. Right? This is what makes it unique. And for the free particle, we'll see the first example of it. For the free particle, V equals 0, right? There is no potential. So if I were to draw this sort of classically, if this is X, right, and this is my particle, there are no potential energy, no forces pushing it one way or another, right? The particle would just run around on this surface. And so when I plug my definition of V into the Hamiltonian, and I substitute all of those variables into the Schrodinger equation, this is the form of the equation you're left with. Right? H psi equals E psi, plugging in the meaning of these things for this specific problem, I get negative H bar squared over 2m, d squared psi dx squared equals E psi. Right? Again, V was equal to 0, so the potential just went away. This is the Schrodinger equation. Right? Step 1 is done. The second step in our process was to solve the Schrodinger equation. And what I want to emphasize to you here is shown in red. When we solve the Schrodinger equation, we're going to get two things: wave functions and energies. Right? This is the eigenfunction. This is the eigenvalue. And so every time we solve the Schrodinger equation, we're going to get these two things. I write this equation in a slightly different form. I think I have it here. Okay. So I take the Schrodinger equation and I write it in this form. Second derivative equals negative k squared psi, where k is defined as follows. So I just moved all of my constants around. And the reason you write it in this way is because it helps us understand how we might solve this problem. If you just look at this, what this differential equation is telling you is that if you take the second derivative of the function, you get the function times some constant. And that might suggest to you a type of answer that you would expect. Right? What kind of function do you take a derivative and get the function back? Well, those are my exponentials. Right? If my function were f e to the alpha x, the second derivative would be e to the alpha x. This is close, right? The issue is that I have a negative k squared. And so you might imagine then, well, the answer's got to be e to the minus alpha x. You should be able to convince yourself that this also doesn't work. The second derivative of this function is also alpha squared, e to the minus alpha x. You get negative alpha times negative alpha. And so it's not exactly clear how you handle it. Right? Well, here's the answer. Right? You insert I alpha x. If I insert an I, the square root of -1, the second derivative of this function is I squared alpha squared e to the alpha x. Right? I squared is -1, so this is e to the minus I alpha x. Right? So when we solve it, these are what we get. Here are our solutions to the Schrodinger equation. We get two things which are written in this form. Right? C1 e to the ikx, C2 e to the minus ikx. If I take that previous equation for k and I rearrange it and solve for e, you get h bar squared k squared over 2m. Right? These are the solutions to the Schrodinger equation. And I'll give you a little worksheet problem where you can convince yourself that this is right. All right, our last step in the process was to interpret. And I need to give you a real quick note here on some complex analysis. Anytime you take a complex analysis course, this is one of the first equations you'll memorize. It's one of the most useful one. It's called Euler's formula. Don't ever pronounce it Euler's. You'll reveal to people that you're a newbie. It's Euler's. And Euler's formula says e to the ikx is equal to cosine kx plus I sine kx. If you want to prove this is true, you can take a Taylor series expansion of all of these terms and you'll see that it all works out. But the reason this is important is because it suggests I can take my e to the ikx function and I can write it as a linear combination of sine and cosine curves. Right? So when you do this, this is called the real part of the function. It has no imaginary components. You abbreviate it real. This is called the imaginary part of the function. It has the imaginary terms, and we call this IM. And if I want to represent what this wave function looks like, right, it's a combination of sine and cosine curves. Here's the real part. Here's the imaginary. I actually have these backwards. I can see this now. This is the sine curve, so this is the imaginary part. This is the cosine, so this is the real part, but you get the idea. Well, which one is it, you might ask, right? Is it the sine or the cosine curve? And what I would suggest to you is that it's both. And a good analogy is to say that we are in effect colorblind. I can't see if it's the real or the imaginary part together. I can only see one of them. I can graph one of them. And at the end of the day, when you see complex wave functions, right, you should think about motion. You get some sense that the particle is moving along here. And you'll see that this contrasts with some problems that we have down the road where things are going to be standing waves. Right? So when you see complex functions, you should think of motion. And I should tell you that these are called plane waves. Right? E to the ikx are called plane waves. We get another critical piece of information, which is this quantity right here. You'll recognize that this quantity right here is the wavelength of the system. And if you do some trigonometry, I hope that you can convince yourself that the wavelength of the particle is 2 pi over k. K is defined up here. The wavelength is 2 pi over k. If k is really big, the wavelength will decrease. If it's really small, it will increase. And I'm going to give you some worksheet problems to explore this idea a little bit. When you think of wavelength, you should think about a quantum mechanical quantity, a variable. And I hope that the worksheet problems help illustrate this ideas to you. But what I want to emphasize to you right now is that in this particular problem, the free particle, there are no restrictions on k. There was nothing which limited it in any way. It could be anything. Right? It could be a big value, it could be a small value, it could be whatever. Right? And because k could be anything, the wavelength could be anything, and also energy could be anything. Right? Remember that k was related to the energy. So there are no restrictions here on the wavelength of the system or on its energy. And that's the free particle. Right? In the next video, I'll contrast that with one which is confined, and I will see you then.